Today we'll explain the IC engine and the Otto cycle. Let's first understand why IC engines are so important. In today's day and age, IC engines power most of the car vehicles and the small scale power generation units like a diesel generator. A common car engine is shown here. So as you can see, these four pistons are actually the part of the IC engine and they power the vehicle. Let's first understand the basics of an IC engine and how it works. So IC engine has a crankshaft mechanism which is implemented with a piston cylinder arrangement. So as you can see here, this is a piston, this is the cylinder, this is the crankshaft mechanism, this is a revolute joint, and this is a revolute joint, and this is the planar joint. So what a crankshaft mechanism does is it converts the chemical energy of the fuel which explodes inside the cylinder and creates a large amount of pressure to force the piston down, and this mechanism essentially converts uh, the oscillatory motion of the piston into rotatory motion, which is in turn transmitted to the load, which can be, say, the tire of the car. Usually IC engines take 4 strokes to complete a cycle, so the entire process of generation of power takes 4 strokes. Strokes refer to the upward or downward movement of the piston.
In this slide, we will be trying to represent the previous shown diagram here in form of PV diagram. The same process can be represented by this PV diagram. As you can see, from 5 to 1, which is the first, is the intake stroke. As represented by the figure here, is represented by the motion of the piston downwards. Next, after the intake of the air takes place in the intake stroke, we have the compression stroke represented by 1 to 2. Here the piston moves upwards. Here in the cylinder we have the air-fuel mixture which is actually compressed. Next we move to the combustion stroke which is represented from 2 to 3. This is represented as a constant volume heat addition process. As you can see here, the piston is stationary and the spark ignition ignites the air-fuel mixture which is compressed. Next we have the power stroke. Here the piston moves downwards and as represented in the color purple from 3 to 4 is the power stroke. The next, we have the pressure release. After all these processes that have taken place, we have the exhaust inside the cylinder. Since the pressure at 4 is much higher than that at 1, there is exit of the exhaust gases from 4 to 1 and there is pressure release. But there is still some exhaust gases left. How are they removed? They are removed in the exhaust stroke from 1 to 5. And this is done by the motion of the piston upwards. Next, I would like to explain few important terms in the IC engine. As you can see here in the diagram, we have 3 important volumes. First, Vt, that is the total volume. It is the maximum volume of the cylinder, also denoted by the formula as equals to the sum of the clearance volume and the stroke volume. But what exactly are these? The stroke volume is the volume that is swept by the piston and represented by Vs. Clearance volume is that small amount of volume that is not swept by the piston or also actually defined as the minimum volume of the space inside the cylinder at the end of the compression stroke, and their sum is the total volume. Another term that is also important here is the compression ratio, which comes late. It's important, may be represented in the next slide. But what is it defined as? It is the ratio of the total cylinder volume to the clearance volume, that is Vt upon Vc. In the last and final slide, we will be explaining how to calculate the efficiency of this entire Otto cycle. As you can see here in the diagram, where 1, 2, 3, 4 are represented. Now these would be used as the basis of defining the efficiency. As everybody of us knows, the efficiency can be defined as simply as work done upon heat supplied to the system. The work done can also be represented as heat supplied minus heat rejected. That is, heat supplied during the process 2 to 3, that is constant volume heat addition, and heat rejected during the process 4 to 1, that is constant volume heat rejection. Hence, the heat efficiency or the efficiency of the Otto cycle can be trivially be written as mCV T3 minus T2, that is from 2 to 3, and mCV minus mCV T4 minus T1, that is heat rejected from 4 to 1, divided by the heat supplied. By eliminating mCV from the equation, all we get is 1 minus T4 minus T1 upon T3 minus T2. Now, as we know, from 3 to 4 and from 1 to 2, both of these processes are adiabatic. Hence, we can write T3 as T4 into R raised to power gamma minus 1 and T2 has R T1 raised to the power R raised to the power gamma minus 1. Now taking out T4 minus T1 and cancelling them, all we get is 1 minus 1 upon R raised to the power gamma minus 1. Here R, as initially defined, was the compression ratio, and hence we get efficiency as its formula. Thank you. I hope this would have cleared some of your doubts related to IC engines.